The surface of the Sun, the photosphere, has a temperature of about 5,500 degrees Celsius. But the corona, the outer atmosphere extending millions of kilometers into space, reaches temperatures of over 1 million degrees. This violates intuition. In most systems, temperature decreases with distance from the heat source. Yet the Sun's outer atmosphere is hundreds of times hotter than its surface. For decades, scientists debated possible explanations. Magnetic reconnection events, Alfvén waves transporting energy upward, plasma turbulence. Observations from Earth and orbit provided partial clues. But remote sensing was not enough. To understand how energy flows into the corona, humanity needed direct measurement. Not of light, of particles and magnetic fields inside the corona itself. The Sun is hostile. Near its surface, radiation and particle flux are extreme. Conventional spacecraft electronics would fail quickly. Heat alone is not the main threat. It is the energy density of solar radiation and plasma. Any mission approaching the Sun must survive temperatures hot enough to melt metal, while keeping its instruments cool enough to function. Earlier missions observed the Sun from relatively safe distances. But to solve the corona heating mystery, distance was the problem. Measurements had to be made within the corona. This required a new type of spacecraft, not one that avoids heat, one that endures it. Parker Solar Probe carries a carbon composite heat shield about 11 centimeters thick. The shield faces the Sun at all times, maintaining a precise orientation. Behind it, instruments remain near room temperature, even while the front surface reaches over 1,300 degrees Celsius. The spacecraft also uses a carefully controlled orbit. Through repeated gravity assists from Venus, Parker gradually reduces its perihelion, its closest approach to the Sun. Each orbit brings it closer than any spacecraft before. Eventually, it entered the Sun's corona. For the first time in history, a human-made object flew through the outer atmosphere of a star. In 2021, Parker Solar Probe crossed the Alfvén critical surface, the boundary where solar wind transitions from magnetically dominated to particle dominated. This meant the spacecraft was no longer just observing the Sun. It was inside its atmosphere. Instruments measured sudden reversals in magnetic field direction, known as switchbacks. They sampled solar wind particles before they had dispersed across the solar system. These direct measurements are reshaping models of how the solar wind accelerates and how the corona is heated. The mission is still ongoing. Each closer pass increases data resolution. Humanity has not landed on the Sun, but it has entered its atmosphere and is measuring it directly. The Sun is not quiet. It constantly releases a stream of charged particles, mainly protons and electrons, flowing outward in all directions. This flow is called the solar wind. By the time it reaches Earth, the solar wind has spread and mixed. It has interacted with planetary magnetic fields and expanded into interplanetary space. But near the Sun, the solar wind is still being formed. This region is critical. If scientists can measure the wind close to its origin, they can understand how it accelerates from subsonic speeds near the surface to supersonic velocities farther out. Before Parker, measurements were indirect. Now, instruments on board directly sample particle velocities, densities, and temperatures within the corona itself. Humanity is no longer inferring how the solar wind begins. It is measuring it at the source. One of Parker's most surprising discoveries was the detection of magnetic switchbacks. These are sudden reversals in the direction of the Sun's magnetic field lines. Instead of flowing smoothly outward, the magnetic field sometimes bends sharply backward before resuming its path. These structures were observed before, but only far from the Sun. Parker detected them much closer to the surface. This suggests they originate in the corona itself. Switchbacks may play a role in transferring energy from magnetic fields into particle motion, helping heat the corona and accelerate the solar wind. The data are complex, but they provide something unprecedented: real-time magnetic field measurements inside the region where energy conversion occurs. This is not observation from a distance. It is in situ physics. Parker carries 4 primary instrument suites. Fields measures electric and magnetic fields. SWAP measures solar wind electrons, protons, and heavy ions. WISPER captures wide-field images of the corona and solar wind structures. ISIS detects energetic particles accelerated by solar eruptions. Together, these instruments build a full picture of the plasma environment. Each instrument had to survive intense radiation and heat. Sensors extend beyond the heat shield when necessary, but retract into its protection during extreme exposure. The engineering challenge was as significant as the science. This mission required instruments that operate in conditions hotter and more energetic than any previous solar probe. The result is the most detailed dataset ever collected from within a star's atmosphere. The solar wind does not stop at the sun. It fills the entire solar system. When bursts of energetic particles reach Earth, they interact with our magnetosphere. This can produce auroras, but also disrupt satellites, communication systems, and power grids. Understanding how the solar wind forms and accelerates is critical for space weather forecasting. Before Parker, models of solar wind acceleration relied on remote measurements. Now, data from within the corona refine those models. Improved understanding leads to better predictions of solar storms. And better predictions protect technological infrastructure on Earth. The mission is not only about astrophysics. It is about resilience. By entering the sun's atmosphere, humanity is improving its ability to anticipate solar-driven disturbances across the solar system. We are measuring the engine of space weather directly. Before Parker, most models of the solar corona relied on remote sensing. Telescopes observed plasma loops and flares. Spectroscopy estimated temperatures and motion. But direct sampling was missing. Parker's measurements revealed that the corona is not smooth. It is highly structured, filled with localized jets, microbursts of energy, and rapidly changing magnetic fields. These fine-scale structures were hinted at before, but now they are measured directly. This changes how scientists model coronal heating. Instead of a uniform process, heating appears to occur in bursts, small-scale magnetic reconnection events releasing energy into surrounding plasma. The corona is not evenly heated. It is dynamic, granular, and constantly reshaped by magnetic forces. That level of detail was not accessible before Parker entered the corona. Humanity now has in situ confirmation that energy transfer in the sun's atmosphere is far more complex than earlier simplified models suggested. One major puzzle was how the solar wind accelerates so quickly. Near the surface, the plasma moves slowly. Farther out, it becomes supersonic. Parker's close passes revealed that energy transfer from magnetic fluctuations, including alphane waves, plays a stronger role than previously measured. These waves carry energy outward along magnetic field lines. As they interact with plasma, part of that energy converts into particle motion. The data show that acceleration begins earlier and in more variable patterns than expected. Solar wind streams are not uniform flows. They are shaped by localized magnetic structures. This forces refinement of predictive models. The sun's wind is not a steady breeze. It is a fluctuating, magnetically driven outflow. Parker's data are now being incorporated into global solar simulations, improving accuracy for forecasting. For decades, physicists predicted the existence of a boundary around the sun called the alphane critical surface. Inside this region, the sun's magnetic field dominates plasma motion. Outside it, the solar wind flows freely outward. Parker directly crossed this boundary. Instruments recorded the shift from magnetically controlled plasma to freely expanding wind. This confirmed theoretical models with real data. The transition region is not fixed. It changes depending on solar activity. That variability helps scientists understand how the sun evolves through its activity cycle. Crossing this surface was not symbolic. It was a physical milestone, measured, logged, and analyzed. Humanity has now mapped a boundary within a star's atmosphere. The sun is not unique. It is a typical star. Understanding how its corona heats and how its wind accelerates informs stellar physics across the galaxy. Many stars emit stellar winds. Some are far more violent than the sun. By studying our own star up close, humanity improves models of stellar evolution, planetary system formation, and exoplanet habitability. Stellar winds can strip atmospheres from planets. They can shape magnetic environments and radiation exposure. Parker's findings refine how scientists interpret data from distant stars. The mission also sets a precedent. It demonstrates that entering extreme stellar environments is possible. Future missions may probe other stars indirectly, using lessons learned here. Parker Solar Probe is not only changing solar physics. It is expanding the methodology of astrophysics. It proves that some mysteries cannot be solved from a distance. Sometimes you must fly through them.